Recording in progress.
Okay, so today we're gonna talk about our heat, momentum, and mass. We're gonna relate these with the concentration gradient, via the diffusivity. So the equations we're gonna be using for each, right? So we have our heat flux, equals our thermal conductivity times our uh, change in temperature over change in position. For momentum, we'll be using the equation shear stress equals the viscosity times the shear rate, which is the change in velocity in the x direction with respect to the y. And then mass, we'll be using J equals the mass diffusivity times the change in concentration of A over the change in position. Um, so first we'll look at heat. Um, so like I said before, it's the heat flux equals the negative thermal conductivity times the change in temperature or the change in position. Now we're trying to get to the energy gradient here. So the way you convert from temperature to energy is using the heat capacity. Heat capacity has the units of joules per kilogram Kelvin. So that gets us to our energy term um, with our temperature. But now we have this kilogram term. So now, in order to remove that, we multiply by our density, which is the units of kilograms per meter cubed. So how we plug that into this equation, right? So we multiply our change in temperature by our heat capacity and our density. And when we do that, we have to divide our thermal conductivity. So currently, our units are joules per meter square seconds equals joules per meter Kelvin seconds times Kelvin over meters. But our new equation will be uh, minus K over rho C times d rho CT over dx. So this essentially doesn't change our equation because we are multiplying it and dividing it. So units here stay the same, right? So these will just come down. And this now becomes joules per meter Kelvin seconds. That doesn't change. And then our density is kilograms per meter cubed. And our heat capacity is joules per kilogram Kelvin. Now, when I said earlier that we wanted to relate everything with the diffusivity has the units of meters squared per second. So that's what we're looking for. So when we go back down here, when we cancel out our joules, we cancel out one of our meters, we cancel out the kelvins and the kilograms. And so now we are looking at meters squared per second. So this negative K over rho C is our diffusivity, and it's our thermal diffusivity, which is denoted by alpha. And then next, we have our change or our unit changes for this term, right? So we have kilogram per meter cubed, joules per kilogram Kelvin, Kelvin, and then meter. So we can cancel out kilograms, kelvins, and now we're looking at joules per meter to the fourth. This is our energy concentration, which is our concentration gradient for the heat. And then this is our diffusivity, right? So that's both these terms up here. Diffusivity is the minus K over rho C. Concentration gradient is the change in temperature times density and heat capacity over the change in position. Next, we'll move on to momentum. So our momentum, like I said earlier, is tau equals the viscosity times the shear rate, which is our change in velocity in the x direction over the change in y. This has a unit, this tau has a unit of force over area. This is kilograms per meter second. And then this has the units of meters per second for velocity over meters. So to convert this one, since it's not temperature, we just multiply by our density, which has the units kilograms per meter cubed. So what we're looking at now, this doesn't change. This becomes viscosity over density times the change in velocity in the x times the density over change in y. So now we're looking at kilograms per meters second times kilograms meter cubed. We cancel out kilograms, we cancel out one of the meters, and we are back at this meters squared per second term. And so this viscosity over density, this is our kinematic viscosity, which is our diffusivity term for momentum. And then when we look at the units for this new term here, right, we keep our meters per second per meter, and we have our density, which is kilograms per meter cubed. We are at now kilogram per meter cubed second, right, because we cancel out. And this is our momentum concentration, which will be our concentration gradient for momentum. And then our diffusivity is this kinematic viscosity term, which is our meters squared per second, which is the same as our thermal diffusivity from the last problem, which is what we're trying to get to. Next, we'll go into mass, which, like I said before, is J equals the mass diffusivity times the change in concentration or the change in position. This we don't have to do anything to, right? This is our diffusivity. This will have meters squared per second units. And this is our concentration, right? Our change in concentration is a concentration gradient. Right, so now we've correlated all these equations, right? So our thermal diffusivity, meters squared per second, our kinematic viscosity, meters squared per second, and then our mass diffusivity, which is meters squared per second. So that's how the heat, mass, and momentum relate based off diffusivity and concentration gradient, right? We have our different concentration gradients, whether the momentum concentration or the energy concentration. So next I'll go a little bit deeper into Fourier's law, right? So Fourier's law is this heat equation that we used to get to our diffusivity, right? So it's minus K times the change in temperature over change in position. Now minus K, so this K value is our thermal conductivity, which is very similar to our thermal diffusivity, right? So this is what we found in the first part, right? We found this alpha and this is K. So what's the difference? Thermal conductivity is how much heat flows through a surface. And diffusivity is the rate at which heat flows. So the big difference here, right, is this is an amount and this is a rate. Um, this this is important, right? We have our conductivity versus diffusivity easy to get confused. The main difference is how much heat is flowing rather than the rate at which heat is flowing. So now I'll dive a little bit deeper into this, right? Excuse me. Heat equals negative K over dt dx. So why is thermal conductivity negative, right? So if we look at a graph here, we have a temperature at 20 and a temperature at 100 degrees Celsius. Okay, this is temperature, this is our position. So our dt dx, right, this is going to be a positive slope, right? But heat flows from hot to cold. That's something that is common sense. So heat flows in this direction. So our total Q will be negative, right? Because our positive, right, we're in the positive X and positive Y being right and up. So our heat is flowing in the negative direction. So that's why this negative is here. And you might be asking, well, what if we are starting hot and ending cold, right? So now our slope is negative, but we are moving in the positive X direction for our heat. So you're thinking, well, slope's negative, so it's going to be negative. But since this negative is here, we have a negative K times a negative dt dx. These cancel out. So our Q will be positive, right? Because this is moving in a positive direction. And since this negative is always there, it canceled out this negative slope, right? Because we're in the positive X and positive Y being right and up. So that is why Fourier's law is the way it is, with the negative thermal conductivity times the temperature over change of position. You can rewrite it, right, with our diffusivity, our thermal diffusivity times the change, and this will be the same thing. Right. So to recap, we related heat, mass, and momentum via our diffusivity, right, of minus K over rho C. Our momentum with viscosity over density, right, which is our kinematic viscosity. And then we have our mass diffusivity, just how it is. And we know that thermal conductivity is how much the heat flows, and thermal diffusivity is the rate at which heat flows. So that will be this video.